Hi, welcome back. This is the second video in chapter 23 on inferences about means. Again, this is one proportion mean or one mean. So let's get started in that second part. This is the problem we just finished. So we've just talked about a confidence interval. Now let's go through all of the steps to do a hypothesis test. So as before, define the parameter, hypothesis statement, assumptions, calculations, and then a decision about based on your p-value, and then a conclusion. This should look very familiar because this is what we've been doing for the last few units. So now let's take a look at a one sample mean and the conditions. So the conditions we need to look at, the sample should be chosen randomly. The sample distribution should be approximately normal. Now, approximately normal means that the population is known to be normal, so we'll actually have to look at again. The sample size is large, meaning it has to be greater than or equal to 30. The graph, the graph that you look at when you graph your data has to be approximately normal, and we'll go through some examples, and that you can look at a probability plot, a box plot, a histogram. Those are the things that we're looking for. So it should be unimodal and symmetric. And then 10% rule, the sample should be less than 10% of the population. And like before, whether or not our standard deviation is known or unknown. And if we do know it, we perform a z-test. And if we don't know it, we perform a t-test. So let's go and show you what that looks like. So this is again when we know what the standard deviation is. So the test statistic is z equals x bar minus mu over the standard deviation of that statistic. And again, this is when we know what our standard deviation is. This should not be new to us. We've seen this before. There's our statistic, there's our parameter, there's our standard deviation. Okay. Now when the standard deviation is unknown, our test statistic is a t equals. But as you notice, most of that is the same. We still have a statistic, we still have the parameter, we still have the standard deviation of the statistic. However, now we have an s instead of sigma. And the s, again, is what we will be calculating. And don't forget about the degrees of freedom is still n minus 1. Okay, so let's go through an example. Example 2. The Fritzy Cheese Company buys milk from several suppliers as the essential raw material for its cheese. Fritzy suspects that some producers are adding water to their milk to increase their profits. Excess water can be detected by determining the freezing point of milk. Freezing temperature of natural milk varies normally with a mean of negative 0.545 degrees and a standard deviation of 0.008. Added water raises the freezing temperature towards 0 degrees and the freezing point of water in Celsius. The laboratory manager measures the freezing temperature of 5 randomly selected lots of milk from one producer with a mean of negative 0.538 degrees. Is there sufficient evidence to suggest, or is there sufficient evidence to suggest that this producer is adding water to his milk? Okay, so same large problems that we had in the last chapter. So let's again go through it step by step. The first thing is to do your or write your parameters and write your hypotheses. So our parameter in this case is the true mean freezing temperature of milk. Our hypotheses, our null, is when it's equal to negative 0.545. An alternative is if it's greater than negative 0.545. Our assumptions, the sample must be random, and again, it was stated in the problem, the sample distribution should be approximately normal. Since it's stated in the problem that the population is normal, then the sample distribution is normal. The sample should be less than 10%. So again, the population should be at least 50 lots of milk, and we will assume that. And we know what the standard deviation is in this problem, so we're going to use our z-test. So since the conditions are met, a z-test for one sample means is appropriate. So our mean value, we know that our x bar is equal to negative 0.538, n is 5, our standard deviation is 0.008, and alpha, again, we're going to use as 5%. So, again, looking at our picture, this is where our shaded region is. It is often helpful to graph or draw a picture. Our formula that we are using, like before in the formulas, is this one. We will substitute in. We know negative 0.538 and fill in our values. Be careful with your division because you'll need your denominator value before you divide. Or you can do that out loud. Just be careful with the extra parentheses. So you should get 1.95 or 1.96 or 1.9565. Since we're looking for a z value, you should use 4 decimal places. So that's again why we go all the way out to the 4th decimal place. We're using a z value or a z-score. We need to do that. And look it up. Our p-value then, and this is again how we write it, probability of z is greater than 1.9565 is a little over 2.5%. So if our p-value is 0.0252, there's 2 things next that we have to do. First is make a decision. Second is a conclusion. Since 0.0252 is less than 0.05, our decision then is to reject the null hypothesis at the 5% level, which then in turn means that there is sufficient evidence to suggest that the true mean freezing temperature is greater than negative 0.545. Which suggests that the producer of the milk is indeed adding water. Now the next problem, I want to just check my time. I think I'm going to come back and do the next problem. The next problem is on page 545 in our text, and we're going to do question 33. But again, I'll come back and we'll do that in our 3rd video.